These are your 5-6 notes on graphing inequalities using two variables. So everything we've done so far, when we talk about an inequality, if we have x less than 3, we are talking about a number line, one variable, one number line, and a graph is on a number line. So now what we're going to study is a linear inequality where maybe x plus y is less than 3. And so if you have two variables, now you have two number lines. So we're going to deal with the coordinate plane. So a linear inequality is a graph representing all the solutions of a two-variable inequality, all of the ordered pairs. There's a boundary line, and that's actually the equation of the linear equation. That's the actual ordered pairs that would fall where they would equal the number. So in the example that I wrote down up above, the boundary line would be the boundary line of the equation x plus y equals 3. So those are all the ordered pairs that would satisfy that equation. These ordered pairs may or may not be included. It depends on if the inequality allows them to equal 3 or not. So we come up with all the ordered pairs that equal 3 in that particular case, like 0, 3, 1, and 2, and then we have to throw them out or not. So depending on whether or not they're included, we have to do something with the graph. It's sort of like our number line. Do we include 3 or do we not? It's a difference between an open circle or a closed circle for when we say that they're equal to it. So we'll do the sort of thing, same display on the coordinate plane. Once you have your boundary line, it creates two different half planes, and they're the two regions that are created by the boundary line. There's a half plane above the boundary line, and there's a half plane below the boundary line. And so if you look at this drawing here, we have two different regions. The blue region is the half plane that's above the boundary line. The blue line is considered the boundary line, so that's the equation. But then everything else is all the values greater than that value above or less than that value below. So we got to include all of those ordered pairs. So just like we did on the number line, when we shade, we're going to shade with the linear graph. So here are the steps in this process. So the very first thing you want to do is you just temporarily want to change the inequality to an equation and graph the boundary line. So if it said less than 3, we're going to set it equal to 3. And then use the inequality to determine if the line should be solid or broken. Now I want to refer back. You probably want to get it into y equals mx plus b if necessary. You don't have to. That's one way of graphing. We'd make a table of values if you want. But the best way is to get it into that form as well. If the inequality is less than or greater than, it should be broken. So we look at the original inequality. If it's less than or greater than, it's broken. That's like our open circle on a number line. The boundary line should be solid if the inequality is less than or equal to or greater than or equal to. So that's our mathematical symbol of saying we're going to include these. And then if it's broken, we're not including those values. When we go to shade, we're going to pick an ordered pair, not on the boundary line. The boundary line is only going to check numbers that equal that number. We want to know the ordered pairs that are either greater than that number or less than that number, depending on what the inequality is. So you pick a point not on the line and you plug it into the original inequality. If the ordered pair gives a true statement, then we know that that's where the solutions lie. If that ordered pair works, then all of those ordered pairs in that half plane work. If that ordered pair doesn't work, if it gives a false statement, then it doesn't lie there. That means that those are the non-solutions. So only one half plane will work. You can't be greater than the half plane or less than the half plane at the same time. Your answer, you don't have to do with a nice set builder notation, which is nice. Your answer is the actual graph. The picture is your answer. So there's no interpretation after the fact. So that's kind of nice. So let's go ahead and try these. So I'm just going to follow that step by step. I think it's good to have your notes open to that page. Follow the step by step. I've got y greater than 1/2 x plus 3. The very first step tells me to rewrite that as an equation. I'm not going to get rid of the inequality. I have to reference it later, but I need to draw my boundary line. This is in slope-intercept form. My slope is a half, and my little b, or my y-intercept, is positive 3. So I'm going to go to my graph. I'm going to start at 3, because that's how you graph using slope and y-intercept. I'm going to count up 1 over 2 for my slope, up 1 over 2, or down 1 over 2 to the left if I want to continue in that direction. I have just created a boundary. And so by making the boundary, I now have ordered pairs that fall above that line, that boundary in the half plane, and ordered pairs that fall below. I notice that the inequality is greater than, and so that right there, I circle it, and I'm going to put a little note to myself, that's why it's broken. Now, I already drew it solid, so to break them after the fact, we just make these little railroad crossings. There's my broken line, and that is the equivalent of an open circle on a number line. Not equal to. We're not going to include all of those ordered pairs. Now I got to shade. I got to figure out which half plane I shade. Are my solutions below this line or above this line? So the next step in those step process is to pick an ordered pair not on the line. A really good ordered pair to use is 0, 0. So unless your line goes through 0, 0, you can use 0, 0. If I check the point 0, 0 in the original inequality, I'm wondering, is 0, 0 a solution to the inequality? So 0, 0 is representing every point in the half plane below that boundary line. So I'm going to take the original inequality, 1/2 x plus 3. I'm going to replace the y with 0. I'm going to replace the x with 0, and I'm just going to check it. Is 0, I'm questioning, is 0 greater than 3? That is a false statement. 0 is not larger than 3, which means 0, 0, it gives me a false reading, so every ordered pair below the line would not work and is not a solution, which tells me all of my solutions are above in the other half plane. So I'm going to graph here all the solutions above the half plane. Now notice I didn't pick a point in this area, but by process of elimination, if the point didn't work that was below it, then all of these ordered pairs above it must work. If you don't believe me, you could check an ordered pair. Let's say this ordered pair right here, which is 0, 4. If I check 0, 4, which is in the shaded region, is 4 greater than 1/2 times 0 plus 3? Is 4 greater than 3? And this is a true statement. So what I'm saying is, if it doesn't work in the other plane, like ours didn't, you shade opposite. The extra point that I just checked is unnecessary as long as you believe me that you did the work correctly. Let's try another problem. X less than or equal to 2. This is one of those one variable terms. We always struggle with these. There is no slope for these. So I'm going to graph the equation x equals 2. And when x equals 2, I write down 2 3 times in a table because I can never remember if x equals 2 is horizontal or vertical. So x equals 2 is 2, 1, 2, 0, and 2, negative 1. And that tells me that my points line up vertically. So this is the boundary line x equals 2. This line right here tells me that it's a solid line, so I'm going to leave it solid, which means those ordered pairs work. Last time we said they didn't work. A solid line on a coordinate plane is equivalent to a closed circle on the number line. Pick a point not on the graph again, so I'm going to use 0, 0 again. 0, 0 is an ordered pair to the left of the boundary line, and so it's going to represent all the points to the left of the boundary line. So when I go to check 0, 0 in the original inequality, there's no place to plug in my y value. But I plug in x is 0, and I get 0 is less than or equal to 2. That is a true statement. And so since 0 is less than 2, I'm going to go ahead and shade where 0, 0 lies. And I just close in this whole area. You can use your pencil. You can use lines. You don't have to shade it solid, as long as I can see. And the shading, what that represents, is all of these ordered pairs, every single one of these ordered pairs. The whole number combinations, the rational, the irrational, the fractions, the decimals, all the ugly numbers, the pretty numbers, all of them. Too many to actually list, So I just shade them all, I color them, and I said if the ordered pair is in that green, mint green area, then it's a solution. I'll try another graph here. X plus 4y greater than 2. So the very first thing we need to do is write it as an equation. X plus 4y is equal to 2. This is in standard form, and I don't like to graph when things are in standard form. So we need to get it in slope-intercept form. So I subtracted x. 4y is equal to negative 1x plus 2. We're going to divide both sides by 4. By doing so, I get y is equal to negative 1/4 x plus a half. Okay, it doesn't scare me that there's fractions, so I'm going to start my line at a half. And I'm going to go down 1 over 4. So I should be in the halfway mark. Down 1 over 4. Halfway through, 1, 2, 3, 4. Up 1, 4 to the left. And here's my boundary line. A 1/4 slope is not very steep. That's why it's almost horizontal. The inequality says greater than only, so we're not going to include these numbers on the line, so we need to break it. And again, I can use 0, 0. The only time you cannot use 0, 0 is when the graph goes through it. You got to pick another ordered pair. So I'm going to check my inequality with the ordered pair 0, 0. I need to see that work because that explains your thinking. Here's the original inequality that you use. You always use the original untouched inequality, unchanged. I plug in 0 for x. 4 times 0 greater than 2 is 0 greater than 2. And that's a false statement. So I am not going to shade where 0, 0 lies. I'm going to shade above. And so these are my solutions then. If 0, 0 wasn't a solution, that means all of the ordered pairs below are not solutions. I use 0, 0. Somebody else might have used a different ordered pair to figure this out. If you pick an ordered pair above, then it should work, and so we'd still shade above. Okay, so there you have linear inequalities. So lesson summary, I'm just curious, if you were to graph y less than x minus 5, would the boundary line be solid or broken? And then I actually want you to go ahead and graph that line or that inequality. Don't forget to shade. Don't forget to look for solid or broken. Good luck.